Chapter 5, Force. The following are a set of problems for you to work on. Pause the video to give yourself time to work on the problems. A tour bus, mass m, is accelerating away from a stop sign at a rate a when a piece of heavy metal of mass 1/6 the mass of the bus falls on the top of it and it remains there. What is the new acceleration? Now pause the video to work on the problem. We can define the equation of motion for the two cases, one for the bus and one for the bus plus the mass. The bus before and after is powered by the same engine, so the two applied forces must be equal. Setting the two force equations equal to each other, we can solve for the acceleration of the bus plus mass in terms of the acceleration of the bus. We find the new acceleration is 6/7 the original acceleration, which makes sense since the heavier bus plus mass would accelerate more slowly. A firefighter of mass 90 kilograms slides down a vertical pole with an acceleration of 4 meters per second squared. Find the friction force that acts on the firefighter. I'll pause the video to work on the problem. In this problem, the net force is not equal to 0. The firefighter is accelerating, but more slowly than free fall. There are two forces acting on the firefighter: the force of gravity pulling him down and the frictional force pointing up, opposite to his direction of motion. The force of gravity is just the firefighter's weight and is equal to 882 newtons. The net force is the frictional force minus the gravitational force. The minus sign indicates the two forces are in opposite directions. But we know the net force. The acceleration is 4 meters per second squared, so the net force is 90 kilograms times 4 meters per second squared, or 360 newtons. Solving the net force equation for the friction force gives 522 newtons. To two significant figures, the answer is 520 newtons. What is the net force acting on a 1 kilogram ball in free fall? Now pause the video to work on the problem. Since the ball is in free fall, the only force acting on it is gravity, and the acceleration is the acceleration of gravity, or 9.8 meters per second squared. Our working equation is F equal ma. Since the mass and acceleration is known, the net force is equal to 9.8 newtons. Two 100 Newton weights are attached to a spring scale as shown. Does the scale read 0 newtons, 100 newtons, or 200 newtons? Pause the video while you think about this problem. The scale would read 100 newtons, the same reading it would have if one of the ends were tied to a wall, instead of being tied to another 100 Newton hanging weight. Although the net force on the system is 0, the tension in the rope within the system is 100 newtons, as shown on the scale reading. A simple rearrangement of Newton's second law gives F net equal ma. Find a net force that is needed to give a 16 kilogram package an acceleration of 7.4 meters per second squared. Pause the video to work on the problem. We have the working equation as F equal ma, and we know the mass and the acceleration. It is a straightforward matter to find that the force needed is 118 newtons. Alexson exerts a steady net force of 58 newtons on a 19 kilogram shopping cart, initially at rest for 1.4 seconds. Find the acceleration of the cart. Find the distance it moved. Now pause the video to work on the problem. The first part is to find the acceleration of the cart. We use Newton's second law and find the acceleration is 3.05 meters per second squared. We may keep extra significant figures for this intermediate calculation. The second part requires the use of one of the kinematic equations from Chapter 4. The displacement is equal to the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. The acceleration is found from Part A, and the time interval is given as 1.4 seconds. This yields a displacement of 2.99 meters, or to two significant figures, 3.0 meters. A racing car travels along a raceway at a constant velocity of 200 kilometers per hour. What horizontal forces act, and what is the net force acting on the car? Pause the video to work on the problem. There are two horizontal forces on the car: road friction acting on the tires and air resistance in the opposite direction. At constant velocity, there is no acceleration. The net force is therefore zero, meaning the force on the tires is equal and opposite to the force of air resistance. Given a mass, M1 equal 10 kilograms, and a mass, M2 equal 5 kilograms, what value of mu sub s, static friction, would stop the block from sliding? Pause the video to work on the problem. Mass M2 supplies the pulling force and is equal to the weight of M2, or 49 newtons. The pulling force is applied to M1. The mass M1 is horizontal to the table, so the normal force is opposite of gravity and is equal to its weight. We are looking for the maximum static frictional force, the maximum force that can be applied just before the object begins to move. The net force is the sum of the pulling force and the frictional force, which are in opposite directions when it explains the minus sign. Since the block is not moving, the net force must be equal to zero. This means that the maximum static friction is equal to the force of the pull. The definition of the maximum static frictional force is the coefficient of static friction times the normal force, which is known. We can substitute the known values in and solve for the coefficient of static friction, which is just the ratio of the pulling force to the normal force. The value of the coefficient of static friction that would just keep the block from sliding is 0.5. The coefficients of friction are dimensionless numbers. They do not have units, so no unit is required when writing the final answer. Your assignments are to read Chapter 5 in the textbook and to watch the videos on Blackboard if you have not done so already. Your homework assignments are due February 16th.